Hey everybody, this is Larry. This is July 1st, I guess. The first day of the July Leetcode Daily Challenge. Hit the like button, hit the subscribe button. I'm going to try to do this every day of this month, and I'm going to do this explanation first. Join the Discord if you want to hang out and ask more questions about this farm or the entire thing or whatever. Anyway, day one, arranging coins. So this problem, it's not hard to see the pattern per se. You see one, two, but not the third one, and so forth. And yeah, and I think the first thing that I thought was, okay, I can do a sort of a linear search. I don't know if it's called, or rather, I don't know if I would call it linear search for reasons that I'll go into later. But you could do that, and it becomes a sort of a simulation problem because you just go from one, two, and then three, and then you keep going until the count is bigger than n or something like that, right? And that's a perfectly fine beginning to the problem. And I did actually solve it that way later on in the live portion where you see me decode it live. But what I would also urge you to do is, well, there's actually a binary search solution. And if you want to pause the video or whatever to kind of give yourself a try, definitely recommend it. Even if you had solved it with the linear search solution. But yeah, the binary search solution notices the fact that you have this function f of x, and if you figure out what the function is, then well, you have to figure out what the function is to make it slightly easier. But the function turns out to be just n choose 2 for whatever n could be, or k choose 2 for how many rows that you have, right? And given that function, well, that function is a strictly increasing function. That's a quadratic equation, and because of that, you could find out when is the first point very easily by using binary search by coming up with a formula. So that's basically what I did. As I actually did it both ways in the linear search and the binary search, so that given k rows, it would require f sub k coins, right? And this is the f of k. As I said, given k rows, it'll take k times k plus 1 over 2 number of coins to be 4 of them, right? And then after that, we just, the binary search criteria is that we're just trying to find a minimum k such that f sub k is greater than or equal to n plus 1. It's actually technically, sorry. I think I did it in a different way. I mean, you'll see why I did it, or I phrased that later. But so this is the f sub k such that this is true, right? But I changed the criteria a little bit to this thing because that's just the way I program binary search. You may have a different internal logic, but for me, I set it so that head is equal to tail, and that I always try to get the last false value, or conversely, the first true value is k plus 1, right? So that's the way that I structure my binary search, and that's how some of these looks a little bit weird as a result, but definitely play around with it, give yourself some practice, and yeah. And this is pretty much straightforward otherwise. It's just an implementation of what we said earlier. Yeah, that's all I have for today's problem. Stay tuned for the live portion, and make sure to hit the subscribe button if you want to follow the rest of the month and so forth. Anyway, have a good month, have a good whatever, and well, actually the live portion will start right about now. Hey, this is Larry, and this is the live portion of the July Leetcode Daily Challenge. Let's get started. Arrange coins. You have a total of n coins that you want to form in a staircase shape, where every cave row must have exactly k coins. Given n, find the total number of full staircases that can be formed. N is a non-negative number and can fit in within the range of a 32-bit int. Okay. So there's a formula for this roughly. You could probably have done do some math for it, but what I'm thinking of immediately is that if you look at these are just the binomial numbers, or the Pascal triangle numbers, or whatever you want to call them. But basically it's 1, 2, 3, 4, and then you could sum it that way. And you can actually do it that way because at most it'll be square root of n times. Yeah. But basically, and you can also do it another way with binary search or something like that if you really want to kind of get the other way to get it a little bit faster. Yeah, so I'm going to try to do it both ways because, well, I want to get it right the first time, but then I also want to just practice my binary search. So let's get started. Let's get it going. So basically, I would do something maybe like for k in range of, actually maybe not even. I'll just do while true. We start with k is equal to 1, maybe on off by 1, but that's okay. So count is equal to k times k minus 1 over 2. Make sure I get the parens in the right place. Is that right? So 1 you get, nope, so it should be plus 1, right? Plus 1 you get 1, okay. And then now, if count is greater than n, then that means that we went over, and then now we could return k minus 1. Otherwise, we just increment k. And then that's pretty much all you need, I believe. But I want to make sure that I am careful with off by ones and exact numbers. So let's try 6, 7, 8. And what I mean by that is that, like, yeah. Okay, so that looks okay. So let's try also a big number. 32-bit int, so we could try 2 billion. I know that 32-bit int could be a little bit, is it unsigned or signed? Signed, so yeah, 2 billion should be okay. And that one's pretty okay. So let's submit it. Get it wrong for like 0 or something, I'll be a little bit sad. But yeah, so that's one way of solving this algorithm. Because this is easy, I'm going to try to upsolve it and just practice my binary search in general. So how would you solve this with binary search or bisection, right? Well, because that we have this formula, we just have to find the first number where this formula is less than or equal to n, right? So yeah, so given k rows, given k rows, it would require let's just call it f sub k coins, is it? Coins, right? So now for binary search, we'll find the minimum k such that f sub k is greater than or equal to n, right? And what is that equal to, right? Well, if you set it to, if you change the formula a little bit to, well, find the minimum k such that f of k minus n is greater than or equal to 0, right? And then now this is a clearer reason of, it will make it a little bit clearer that, and we know that f of k is monotonically, or strictly even, really strictly increasing. So what that means is that f of k will always keep going up, as you kind of maybe have an intuition for. And so yeah, so that's pretty much all we need to do the binary search. So let's upsolve this a little bit. Let's write the depth of f of k, or yeah, and then we just return the k times k plus 1 over 2, right? And then now we start with head. I always call them head and tail. You could name them however you like. So tail, we know that it's roughly the square root of, like, for 2 billion, okay, I actually forgot what it was. But I think but you just pick a big enough number, right? And that should be okay. As long as it's bigger than the square root of 2 billion minus some constants. So, and the only thing to watch for here is that you may get overflows, because we're going to put these numbers into f sub k. So in other languages, in Python it won't come up, but in other languages you might overflow, so you have to be careful in how you choose this, and also how you, because you're calculating n squared, essentially, or k squared in this case. So yeah, so while head is greater than tail, we want to find the first instance that this is true, which we can also say we want the first instance where this is false, maybe. That'll make the search a little bit straightforward for me. So yeah, so mid is equal to head plus tail over 2. Yeah, if f of mid minus n plus 1 is greater than 0, if this condition is satisfied, that means that we can go lower, right? Because that means that if this is true, that means that this is not the min, that this, or it could possibly be the min, but we have to go lower so that the min can be lower. So tail is equal to mid, else head is equal to mid plus 1, because if it's already true, then sorry, I think I might have done this a little bit backwards. That's why I always say it out loud. This is more practice for me. But okay, so if this is true, if this is true, that means that if this is true, that means that the min could be minor. Yeah, okay, no, this is right. Just I said in awkward ways. Yeah, because this is increasing, yep. And then at the end, I think we just need to return head, because head is equal to tail in this case. So it doesn't really matter which one you do, but... So yeah, of course there's an off by 1, so we have to be a little bit careful. Maybe that's... So let me think about this. So we do have an off by 1. I thought that this would be helpful enough, but this is why I always give myself the opportunity to practice the things that I need to be good at, because, yeah. Oh, I think I just did it the wrong way, did I? Maybe not. Yeah, now this is the right way, but now we have to minus 1. That's why, yeah. It's a little bit weird the way that I did it, but that's because we're trying to get, at least for me, the way that I like to structure it is such that the first number, to get head in such a way such that head would be, what you might call it, head would be the first case in which, the last case in which it is false, and this is why I have it structured this way. Let's give it a submit, because I'm still not confident about this, to be honest, but I think, yeah, that looks okay. But that's why I practice it. To be honest, for me, I still struggle sometimes with the off by 1s and converting it strictly from, but I try to keep it the same way, and sometimes you can play around with it, but I frame it so that it is the first, so that head would be the first case in which the last case in which it is false, and head plus 1 is the first case in which it is true, and then you think about how to invert it in that case, and apparently this is how I did it, but because this is this plus 1 plus 1 or something like that, right? Oh, oops. Anyway, yeah, so the complexity for this problem, it's hard to give a precise meaning thing. We can analyze it in terms of n, but the disclaimer here is that in a lot of these type of problems where the input is an integer, technically speaking and pedantically speaking, n is the size of the input, not the input itself, and the size of the input is in terms of the number of bits, right? So usually if you think about complexity theory and stuff like that, that's what they talk about. So yeah, but for the purpose of just going through this, and just doing an explanation, and just communicating it, I would maybe choose another variable. But given in this n, lowercase n, the binary search will be roughly O of n. You can actually make this just n because you know that it's going to be square root of n, so it's going to be strictly less than n. And then here is just log n, right? Because it is binary search, and this function is roughly O of 1, pretty much. This assumes constant bit integers and stuff like that. But yeah, if you did it the other way, then with what we said with the linear search, quote unquote, would be square root of n, because it just goes up to the square root of n, roughly, give or take, because that's how you solve this. But yeah, that's all I have for the implementation. Obviously, the space is all one, but I recommend practicing with binary search if you didn't get it, or even if you did get it without binary search, because I think this is really good practice. I take practice anytime I get, because I still make mistakes, and I still have to think about it for an extra second, as you kind of saw. So yeah, that's all I have for this problem, the live portion, and I will see y'all tomorrow. Bye bye. After I find a button.